Hello, in this video we will talk about balancing redox reactions in both acidic and basic solutions. So why do we need to do this? Well, you can write a reaction that's balanced with respect to atoms and elements like we have here, but it's not balanced with respect to electrons transferred. So in this reaction, electrons are transferred from the reducing agent to the oxidizing agent. And well, if you look at the oxidation states, you'll see, all right, iron goes from 0 to +3, each chlorine goes from 0 to -1. So, all right, here's the oxidation half reaction, here's the reduction half reaction. This number's 3, this number's 2. They don't match, right? So in this actual process, the amount of electrons lost by the oxidation step needs to be equal to the amount of electrons gained in the reduction step, and right now they're not. So this reaction is balanced with respect to elements, but not with respect to charge and electrons. And in a redox reaction, you need to be balanced with respect to both. Otherwise, it doesn't really make sense. So we need to figure out how to do such balancing. Now, for this reaction, it's pretty straightforward. So you can balance it by inspection, it's called. And so that means you just look at it and see what you got to do. Well, I got 3 electrons, I got 2 electrons. The lowest common multiple of 3 and 2 is 6. So I need to make both of these 6, and then I can add them together. And so what we do is we multiply each half reaction by some factor. And when we do this, it means we distribute this factor all the way in. So there will be 2 irons, 2 iron 3+, and 6 electrons. Then over here, to make 6 electrons, we have to multiply by 3. So that gives us 3 chlorines, 6 electrons, and 6 chloride ions. Now, once we've done that, we can then add these together. So here's what they look like after multiplication. And we can add them together and then cancel the electrons, because it's the same on both sides, as it should be. And then, ta-da, here is our balanced redox reaction. So this looks different than what we started with, but now it's balanced with respect to both atoms and charge. And so you can double check this by counting atoms. You know how to balance reactions for that. You can also double check it by balancing charge, or checking the charge, right? So let me look at before. Before, overall, the charge on the left side is 0. Charge on the right side is +3, -2. So the overall charge here is +1. Your reaction can't go from 0 to +1 because, well, it needs to be neutral. You can't just magically gain or lose charge, right? We're trying to describe that process, and you can't just magically change that. So now in our balanced reaction, the overall charge on the left is still 0, but on the right, you have 2 times +3, that's +6. Here you have -6, so the overall charge on the right side is also 0. So the charge on the left, charge on the right need to match, and we did that. So this one's ready to go. Now this is a pretty simple reaction, so you can just look at it. You can imagine it gets more complicated, and we need to talk about how to do that. So there's a plan. And ultimately, you'll need to know how to do this plan. I try to simplify it, and you can probably simplify it even more in your head to help you follow the plan without the directions. So the first thing you do is you figure out what's oxidized and what's reduced, and you pull them into half reactions. We've done this before. And I typically add electrons at this step. That's what I like to do. Your textbook, Macquarie, adds the electrons later. It doesn't matter. Now you got to go balancing things. And so you balance each half reaction first, and then you add them together at the end. And so each half reaction, first you do atoms other than hydrogen or oxygen. And then you balance the oxygen, then the hydrogen. So you balance the oxygen by adding water. We're doing these reactions in aqueous solution, so there's water everywhere. And if you need to add or lose oxygen atoms, you're going to get them or put them on the water. So the water plays a big role here. And then in an acidic solution, you also have H+. Technically, you have H3O+, but it makes our life simpler to just call it H+. And so we'll do that. And so you can use that to balance the hydrogen, because that makes sense. In an acidic solution, if your reaction needs more or less hydrogen atoms, it can pull them from the acidic component of the solution. All right. Atoms, oxygen with water, hydrogen with H+. Now, put the electrons in if you have not already. When I get here, I've already done it, but if you haven't, put it in. Now, the thing we just did is we made the number of electrons match, right? Each half reaction needs to have the same number of electrons lost or gained, and so you have to adjust the half reactions to do that. And you do that by multiplying by an integer and distributing it all the way through. Then you add things together, and then you cancel or combine things that are the same on both sides. The reaction before, we canceled out the electrons. At the last example, we'll end up canceling out some other stuff too. And then finally, check your work, right? You can check the atoms, whether you're balanced in respect to that. You can also add up charge on both sides and make sure that's the same. It doesn't have to be 0, but it needs to be the same on both sides of your reaction. All right, so this is acidic solution. Now, when you go to basic solution, you don't have H+, so we have to do something different. So in a basic solution, you add hydrogen by adding both water and hydroxide. So if you added water to one side, say the left, and you add hydroxide to the right, your net gain here is one hydrogen atom on the left side, right? So you add 2 hydrogens to the left and only 1 to the right. So you use this like pair, equal amounts of water and hydroxide, in order to add hydrogen to one side or the other. Kind of makes sense. You don't have H+ to play with, but you do have hydroxide and you do have water. So everything else goes the same from here. So your textbook has a table about this, and I want to point out that in, say, some older or maybe even current printings of this book, even all within the 4th edition, you may have an incorrect method listed here. So as far as I know, this is the correct method according to the publishers. I mean, what I'm telling you is right, so irrespective of what they say. And it's a difference between steps 3 and 4. So just keep that in mind if you're looking at the textbook, which you should be. All right, so now let's do some examples. I got 3 of them here to try to demonstrate this. And so first we have hydrogen peroxide and iron in an acidic solution, right? We typically just say acidic over here. So first thing we got to do is find oxidation states. We've done this before, so I'm not going to show it again. So here are the oxidation states. And then we have to find the half reactions. Well, iron loses electrons, so it's oxidized. And then hydrogen peroxide, the oxygen in here, gains electrons, so it's reduced because its charge goes down. Okay, then I also tend to put the electrons in, right? Iron 2+ to iron 3+, you're going to lose 1 electron. And then hydrogen peroxide, well, it's a little weird here because we don't have the same number of oxygen atoms on both sides. But just looking at the reactants, each oxygen is going to gain 1 electron, and there's 2 oxygens here. So I'll put 2 electrons in. All right, so now we can go on. The oxidation half reaction is already balanced, so we don't need to mess with that now. But the reduction half reaction, well, we don't have the same number of oxygens on both sides, so we need to fix that. And the way we balance oxygen, remember, is we add water. So we can add 1 water molecule to the right side, and then now we have 2 oxygen atoms on both sides. All right, so we've done the oxygen. Now we gave ourselves a new problem, though. Now there's 4 hydrogens on the right and only 2 on the left, so we need to balance the hydrogen. In acidic solution, you can just add H+, and so now we do this. There's a total of 4 hydrogens on both sides, so that's great. And we've now balanced the reduction half reaction. Now we can put them together and then realize, we only have 1 electron in the oxidation half reaction, but we have 2 in the reduction. So we need to multiply the oxidation half reaction by 2 to make this match. Then we can add it together, and we'll cancel out the electrons because they're the same on both sides as they need to be. Then for this reaction, nothing else needs to be canceled out. So great, we're done. All right, let's do another example. Let's balance this reaction, also in acidic solution. So the first thing we have to do is oxidation states. Again, you've done that before, so I'm not going to talk through that now. And then we pull out the half reactions. So the copper loses electrons, so it's oxidized. The nitrogen in the nitrate is reduced, and so that's our reduction half reaction. Now I like to add electrons next, so let me do that. So to the copper, it loses 2 electrons, and there's only 1 copper, so that's great. For the nitrate, well, each nitrogen atom goes from +5 to +2, so that's gaining 3 electrons, and there's only 1 nitrogen atom, so that's fine. Okay, now both of these are balanced in terms of atoms other than oxygen and hydrogen, so we don't need to do that. But the reduction half reaction is not balanced in terms of oxygen, and so we'll need to fix that. And so we fix that by adding water to the right side, so that now there's a total of 3 oxygens on the right side, and then there's 3 on the left. Now we have to figure out the hydrogens, and so we have 4 hydrogens on the right. That means we need to add 4 hydrogens on the left right here. Now we're balanced in terms of hydrogens and all the other atoms, so we're good there. So now we put these together and we look at the electrons, And we have 3 electrons in the reduction half reaction. We have 2 electrons in the oxidation half reaction. So we need to get these both up to 6 in order to reach our lowest common multiple. And so you distribute a 3 through the oxidation, a 2 through the reduction, and then you add them together. And then you get the following result. Now, getting down to here, I canceled out electrons on both sides, but then there weren't any other atoms I could cancel or combine, so that means we're done. Good time to double check. Double check you have the same number of all atoms on both sides, and you have the same charge. So the charge needs to be the same on both sides, but it does not need to be 0. Okay, you have 8 hydrogens on the left and 2 nitrates, so overall this is a +6 on the left. Then on the right side, you have 2 for each copper, and there's 3 of them, so this is a total of +6. So both sides have a charge of +6. As long as they're the same, that's okay. In the real world, that means there must be some negative counterions around in solution in order to make this possible, but we omit those because they just clutter up the reaction. So we tend to do this net ionically, and it makes our life so much easier. But you do need to recognize there are some negative counterions in there. Okay, last example. So now we're doing one in basic solution. And, well, we go through our normal process. First, we find the oxidation states. And now for this one, you can't just find the oxidation states because you don't know what to do with carbon or nitrogen, because carbon and nitrogen are not on our table, what we talked about in terms of priority order for oxidation states. And so for this one, you have to do Lewis structures to figure it out. So this is beyond what I'm expecting you to do in this class, but I want to include it here because I think it's interesting and it's worth showing at least once. So you take the Lewis structure for cyanide, and when we're counting for oxidation state, all of these shared electrons in the middle, all 6 of them, we're going to assign them to the most electronegative atom. And so if we pull electronegativity values out of the book or a table, we'll find that nitrogen is more electronegative. So that means all 6 of these electrons go to nitrogen, all 6 of them. And then it has these 2 lone pairs. So that means total here, nitrogen is assigned 8. This is much different than when we did formal charge in the first semester, where we just split these shared electrons. But here we're assigning them all to nitrogen. So this means that the oxidation state on nitrogen goes like this. So we have 8 electrons assigned to it in the molecule, and nitrogen came with 5 electrons in the free atom. So that means the charge on here is -3. So we'll put that on top of the nitrogen up here, -3. Now then you can figure out the carbon by either looking at the whole molecule and then it must add to -1, or we can look at the Lewis structure. All right, so carbon does not get any of these shared electrons, but it has the 2 lone pairs, or the 2 electrons from the single lone pair, I should say. And so that means carbon comes with 4 electrons, and here it has 2, so that means carbon's +2. So we can throw that up on top as well. Now for the permanganate, you can figure that one out more straightforward. It's each oxygen's -2, and then that makes the manganese +7. For the OCN, you have to do Lewis structures again and use the electronegativity values. So oxygen's the most electronegative. It's got 8 around it because it gets both of these shared electrons. Apologies for the crappy Lewis structure that I stole off the internet. And all right, so oxygen normally has 6 valence electrons. Here it has 8, so that makes the oxygen -2, not a surprise. Then the nitrogen over here has the next highest electronegativity value, so it gets all 6 of these shared electrons and the 2 from the lone pair, so that makes nitrogen -3, like it was before. And then the carbon here, effectively it has no electrons in this structure, because these 2 and these 6 go to other places. So carbon comes with 4 valence electrons, and now here it has 0, so that makes carbon +4. So carbon is oxidized. And then we can figure out the manganese dioxide by just knowing what oxygen is, and then manganese gets the rest. So manganese is reduced. All right, from here, now we can go about our plan. So we want to write and balance the half reactions. So we'll do oxidation first. So here's oxidation. Carbon goes from +2 to +4, so it loses electrons. And then I just throw down the whole molecule that's up in the equation. Right, we're off by an oxygen atom, and that's okay, we can fix that. First, I'm going to add electrons. So carbon loses 2 electrons, so it's a product. And there's only 1 carbon. Now we can add water to fix the oxygen. So we just need to add 1 water molecule to the left because there's only 1 oxygen on the right. Now we've added H+, so we need to fix that. Before, we just would add H+ to the right side, but we're not in acidic solution, we're in basic solution. So what we do is we add hydroxide and water, the same number to both sides, and then use that to, in effect, add hydrogen atoms. So we need to add 2 hydrogen atoms to the right side over here. So we add 2 waters, which is a total of 4 hydrogen atoms to the right. And we add 2 hydroxides to the left, which is a total of 2 hydrogen atoms. So the net effect here is adding 4 hydrogen atoms to the right. In doing so, now you have water on both sides, which is kind of a little weird. You could cancel this out now, and that would be fine. Or I'm just going to let it ride, and I'll cancel it out at the end. Either one is okay. Okay, now we need to do the reduction half reaction. Permanganate goes to manganese dioxide. And now each manganese is gaining 3 electrons to go from +7 to +4. So we put that in there. There's only 1 manganese. This reaction is balanced in terms of manganese, so now we need to just figure out the oxygen, and thus the hydrogen. So we're going to add water to the right side to make 4 oxygen atoms on both sides. Then we need to deal with the H that we just added. And so to do that, we add the water and hydroxide pair, and we put water on the left so that we get more hydrogens on the left. And so this, in effect, adds 4 hydrogens to the left side of the equation, which is what we want. And again, we could do some canceling here if you want of the water molecules on both sides. I'm just going to let it ride and throw it all together next. So next thing we got to do is make the number of electrons the same. So here are our 2 half reactions that we just were talking about. And we have 3 electrons in the reduction, 2 electrons in the oxidation. So we're going to have to bring both of these up to 6. So we distribute this number all the way through. Don't forget to, for example, take this 2 and put a 2 here, put a 6 here, put an 8 here, because you're distributing it through 2, 4, 8. Do that kind of thing. So do that, and then add them together. And then that gives you this mess. This looks kind of like a mess, right? There's all kinds of stuff everywhere. And that's okay, we can fix it. So we're going to cancel some stuff out. We're going to cancel out the electrons on both sides. We can cancel out some of the hydroxides and leave 2 hydroxides on the right. Then we can think about the water, 3, 8, so it's 8, 9, 10, 11 waters on the left, 10 waters on the right. So we'll just leave 1 water molecule on the left and none on the right. That kind of thing. I think the other stuff is okay. So you do that, and then you add them together. So we have our 1 water molecule on the left, 2 hydroxides on the right. Everything else is balanced. You can also double check the charge too. Overall, the charge is the same on both sides, so that's good, and we're done. So this seems like a long process, and it kind of is, but you can simplify it by remembering the following. All right, oxidation states to half reactions. You know how to do that. And then, put the electrons in when you make the half reactions. You've already done that. Then you balance each half reaction separately first. You do other atoms, then oxygen, then hydrogen. And in acidic solution, the hydrogen is adding H+. In basic solution, the hydrogen is added by water and hydroxide. Then you add them together and make the number of electrons the same, and then cancel out the terms. And then always double check. Right? So once you do a few of these, you'll get used to the process, but you might have to do 5 or 10 of them in order for it to really sink in how to pull it off. One final thing I want to say is there are several different methods by which you can balance redox reactions. Ours is called the method of half reactions. Okay. You can also use the coat hanger method, and there's a couple other ones. So if you see somebody doing something else, as long as you get to the same answer, then it's okay, right? This is a results-oriented problem. As long as you get the right result, it's okay. Great. Well, thanks for watching.